is a member of the String Theory and Gravitation Group, or STAG, in the Department of Mathematical Sciences at the University of Southampton. Before arriving in Southampton, initially as an STFC Ernest Rutherford Fellow, he was a researcher at the Perimeter Institute for Theoretical Physics in Canada, at the Kavli Institute in California, at the University of Barcelona, and at the Commissariat for Atomic Energy in France. He does research on black holes and holographic dualities, which is what he's going to be talking about tonight. Please welcome Dr. Oscar Diaz.
So first of all, let me start by thanking William for organizing this series of talks. This is something that I really find quite amazing here in the UK, is that people get engaged with outreaching, which is not common outside the Anglo-Saxonic world. Trust me, because I'm from Portugal, I lived in Spain, and there, people don't care about outreaching. First thing, can you understand me? Because my accent is, I'm sorry, I have already lived 8 years, in English-spoken countries, but I don't get it, In my defense, even in my hometown, people at a certain point, asked me whether I was Portuguese or not, after hearing me talking Portuguese, so I guess that I have really a problem with languages. But hopefully you can understand me. So I should say that I was not sure of what kind of audience and expertise I would find. And it is extremely difficult in such situations, to prepare a talk. But hopefully, I did something that you will enjoy, okay? So the title of my talk is Black Holes as Bubbles of Fluid. Because I will tell you about certain connections that there are between black holes, which are astrophysical gravitational objects described by the Einstein theory, and something that seems to be completely different from a black hole, which are soap bubbles and liquids and gas. Okay? But there is a connection between them, and I guess that although you are on top of everything that is going on out there, maybe you have not heard about this, because this is relatively recent, and so maybe you will get some interest. On the other hand, because I'm going to talk about two completely different things, it looks like that I'm squaring the sphere, because we'll be discussing two completely different objects. So, this sphere in particular is something that you can find in Montreal in Canada. This is an island where you have a Formula 1 race every year. This is an island that is artificial completely, and this sphere is over there. This building is over there. So what I want to talk today is I want to talk on one hand about black holes. Then I want to tell you that there is a one-to-one correspondence, also known as duality, between black holes and fluid dynamics. That goes by the name of holography. This is something that has been being developed in the last 15 years. And because black holes are related with fluid dynamics, and turbulence is something that happens quite often with fluids, this means that black holes are also related with turbulence, and actually are nowadays also being used to study certain aspects of turbulence. So eventually I will talk about all these topics today. Maybe I will not arrive to turbulence because I prepared too many slides, but at least I will talk about these three ones here. Okay, so what I want to emphasize is that there is a relation between these four topics that seem to be completely far apart from each other. But before we can arrive to this one-to-one map, this relation between these topics, I will have to talk a little bit about black holes. And in particular, I will have to emphasize that black holes, in spite of their name, they are not that black in the end of the day. Although this is probably something that you know quite well, because this is one of the most important lessons that Stephen Hawking gave to us. Okay? So let me start with this picture. This is in Antarctica, in the South Pole. This is a real lab that is there. and I guess that some people have to live there at least during a few months to do the experiments. And now the nice thing on this picture is that on one end you can see the northern lights, which I guess that here you should call them southern lights. I don't know if you do call them? Okay. And now the nice thing is, I don't know if you can see from the back, but do you see that there is also here some purple color? So this is the Milky Way, our galaxy. And the amazing thing is that we are on the Earth, we are a little dust in the middle of our galaxy, and nevertheless we can take pictures like this one, where we can see that there is a lot of things out there. And in particular, this Milky Way, so is something that it's a galaxy, it's a spiral. We know that at the center of this galaxy there is a supermassive black hole that is basically keeping all the solar systems that are in our galaxy orbiting around this central region. This black hole has something like 1 with 9 zeros in front of it times the mass of our Sun. That's how supermassive this guy is. And we live somewhere here. Okay, this is where the Sun here is, and the Earth is orbiting around the Sun over there. And what happens is that, if you think, if the top of this desk is the plane where the galaxy, where the arms of this spiral galaxy are, what happens is that the solar system, or the Earth, if you want, is rotating with a certain angle with respect to the top of the desk. And this is the reason, if we are here on the top, we can have a view of the Milky Way. You see, we can have a top view and take pictures like this one, where we can see the plane of the galaxy. Although we should be in the middle of it, and so when we are in the middle of it, and I look like this, I just see the person that is in front of me. But from the top, I can see, the wide picture. Very well, guys. And in particular, I don't know if you have ever seen this. How do we know that there is a supermassive black hole in the center of the galaxy? Well, we know it because, in particular, there is some observations that have been happening in the last 20 or 30 years that have been observing the motion of certain stars that live nearby the center of our galaxy. And from the movement of the stars, we know that there should be something supermassive that is keeping the stars orbiting around this central area. But then we look to that central point where something supermassive should be, and we see nothing. Nothing. There is nothing there. At least our eyes or our telescopes do not capture any object there. But because of the movement of the stars, if there was nothing there, the stars would basically go along a straight line. In the same way that the moon, if the Earth was not here, the moon would, it has some velocity, it would just keep going more or less along a straight line. But because there is the pull of the Earth, the gravitational attraction of the Earth, what happens is that the moon is attracted by the center of the Earth and goes around it. Okay, instead of just keeping going on a straight line. Okay, so here it's a similar thing. We will see. I will show you this big star. It's where we think that the supermassive black hole is. Then each one of these guys, are kind of stars, bright stars that we can see with our telescopes. And now what I will show in the next video is what has been happening along it's a series of photographs along I think several years. And you will see that some of the stars, they will, for example, one of them will do something that is like this. It is coming like this, more or less on a straight line, and suddenly it goes up. It turns around and goes up. Which means that there is really a lot of gravitational attraction there. So let's see if this works. It is. So you see, look at this yellow one. This yellow one was going along a straight line, you see, as if there was nothing, and suddenly it did a 360 turnaround. This means that there must be something really strong pulling. Okay. We show it again. Here we have. So you see, but you also have the orange one. You also have this blue one, and it's like it's with observations like this one that we know that there must be something very massive there. But on the other hand, we cannot see it with our telescopes. So it must be an object that does not reflect light or does not emit light at all. And our best candidate is a black hole. Not necessarily, but it's one of our best candidates for sure. Okay, so what I'm going to show next, and it's an illustration, okay? It's not a real picture. But this is how we imagine a black hole. So we have, we look to the sky on a dark night, probably on Antarctica, so that there are no artificial lights. And what we see is a cluster of galaxies. Each point here is probably a galaxy with a lot of stars inside of it. And the way we imagine a black hole is something like this. Something that is extremely dark, okay? And that destroys our view where it is, right? Because here around it we see all the lights that are coming from all the galaxies. But here, if we are close enough, we will see a dark spot. Okay? But on the other hand, you will notice that although this is an illustration, it's an illustration with, the guy that was doing this illustration, he knew a little bit about black holes. So you will see that there is some light concentrated here around the black hole. As if you are concentrating a lot of light there, because the light that you have here, it's clearly, you have more light there than you have, for example, in this region. And the reason why this happens is because black holes, they behave as gravitational lenses. If we don't see very well, or, I don't know about you, but when I was a kid, I used to be a bad kid because I would take, a magnifying glass. What do you call it, magnifying glass? And I would start burning things, because the magnifying glass or a lens, what it does is that you have light rays that hit it, it's a disc, and then they focus the light on a certain point, right? So what is happening here is something like that. So we are here on the Earth, okay? Here is the black hole, this guy. Over there it's the cluster of galaxies, billions of or millions of galaxies. Now each one of these galaxies sends a light ray or light rays to the Earth. The problem is that our eyes are a little bit stupid, I'm sorry to say that, because our eyes can see the direction that the light has when it hits our eye. It can identify if the light is coming from there or from there, okay? But it can only recognize the direction of the light when it hits our eyes. It does not know where it came from. And what happens is that if you have something that is supermassive there, Einstein told us with E equals to mc squared, he told us that light is energy. And if light is energy, that means that light is mass. And any energy or any mass is attracted by a gravitational field. Now, if you have a black hole that has a huge gravitational field, this means that if you have some light from here that was sent, imagine it was sent on this direction, okay? One was going in this direction and another one was going in this direction. So it would not hit the Earth. But because the gravitational force of the black hole is huge, it will bend the light. So the light started by going like this, but very much like the stars in the previous slide, they will get bended when they go through the black hole and they will hit the Earth. In this sense, it is a lens, you see, because the light was coming like this, but when it hits the lens, it bends it and focuses it on a certain point. So what will happen is that you will have light rays coming from there, hitting the Earth, but you will also have this white one, which is a light ray that your eye will think that is coming from there, but in practice came from there. So you see, in the same point, you will have a concentration of light that is coming actually from many different regions in our galaxy. And of course, this concentrates a lot of light because you are receiving light from there, but also from there, and so on. Okay? And this is an effect that was already observed also by telescopes, okay? Although again, we cannot see this guy, but we can see this gravitational lens effect. Very well, guys. And now the next thing that I want to tell you is that, yes, this is the image that we have of a black hole. A very dark object. But in the end of the day, we know already, since the 70s or the 80s, with the work of Stephen Hawking, that black holes are not that dark. And the reason they are not that dark is because of quantum effects that happen also in the neighborhood of a black hole. And in particular, quantum physics, even without black holes, without gravity at all, tells us that what we call the vacuum is not really empty. You know, I guess that the Greeks, they created the word vacuum to describe something that has nothing on it. But they were completely wrong. Okay? Because vacuum, as we know it, we know that it is completely populated by what we call virtual pairs of particles. We call them virtual pairs because they exist only during a short, extremely short period of time. So this, you out of nothing, just because you have some quantum fluctuation, you can create two particles. One is a particle, the other one is an antiparticle. So one is an electron and the other one is a positron, for example. And these two particles, they live during a small, infinitesimal amount of time, and then they annihilate, they collide with each other again, and they annihilate it again. And they disappear. But this keeps happening, you know, in any point of the vacuum. And this keeps happening as time evolves. So there is some action going on. It's not empty. It lives during a short period of time, but you have so many of these happening, you know, out of nothing, you create a particle and an antiparticle that then get annihilated. But this is happening in every single point of what you are calling the vacuum. So there is a lot of action going on. In particular, how do we know that this is for sure happening? Because there is a way of making these virtual pairs of particles real instead of virtual. What do I mean by real? By real, I mean that I don't let them get annihilated in a short period of time. And like this, I keep them alive and separated from each other during a sufficiently amount of time so that I have time to prepare my camera and take photographs of it. Okay? And how can I do that? I can do that, for example, if I have an electric field. If this particle has a certain electric charge, the antiparticle, the red one, will have the opposite charge. And this means that if I have, for example, an electric field, the positive charges will be pulled in that direction, in the direction of the electric field. There is an arrow there. But the negative, the antiparticle, will be pulled in the opposite direction because it has negative charge. So what happens is that these two guys, they popped out of nothing, and then they would annihilate. But because I have this electric field that basically it's one pair of ends, one pulls the blue one to the left and the other one pulls the red one to the right. And so I'm not allowing them to annihilate. Actually, I'm splitting them even further. Okay? And then I can observe these two guys independently. Okay? That's why I know that, and they were not there before. So I know that this is really happening there. Now what Stephen did, and was quite amazing, is that he said, look, I don't really need to have particles that are electrically charged. I can just have a particle and an antiparticle. They might not even have electric charge, but if they are next to a supermassive object or a massive object, gravity itself should be able to split them apart. Because, one of the particles might be closer to the center of the massive object and the other one a little bit further away. So this means that the red one will be pulled with more strength than the blue one. And if I have something that is closer to the center is on the bottom. This one is being pulled more than this one. This one is also being pulled to the center, but because this one is being pulled more, they will split. Sorry, I did not do the right movement. So both of them are being pulled down. But because this one is closer, it will be pulled more with more strength. So the distance between the two will increase as time goes by. And in particular, it might happen that this red one ends up being absorbed by the black hole. It enters inside the black hole and we never hear about it anymore. But the blue one might even escape to, let's say, to this point where we are in this room and we can see it. And so for us that are in this room and that receive this blue particle, it will look like the black hole has emitted some radiation. It is as if, this blue particle came from the black hole towards us. Okay? And remember, here I'm putting them sufficiently separated, okay? But this is happening, in the neighborhood of the black hole. And actually, here, one of the particles has positive energy or positive mass. The other one has negative energy in practice. So this is what is the positive. Instead of positive and negative electric charge, you have positive energy and negative energy. This can happen in the quantum physics realm. Okay? And so the negative energy is swallowed by the black hole. We never see it again, but the positive energy reaches us and we measure it. And so the black hole in practice is not as dark because it is emitting what we call thermal radiation or thermal Hawking radiation. Okay? Of course, this radiation has very small energy. Or if you want the temperature of the black hole, typically it's very small, so it's not easy to detect this radiation. Okay? Our detectors have to be extremely sensitive in order to capture it. Okay? And of course we should also have a black hole a domesticated black hole, that we could do experiments, stay there and stay there but sufficiently far apart so that you don't hit me, and now let me do some experiments with you. Very well, guys, I will not have many formulas, I will just have two formulas in this talk, okay? But they are sufficiently important to have them. I want to show you them because especially one of them is really wonderful because it's the only time that we have ever seen it in science. But before I get there, let me just tell you that because the black holes emit these particles, these Hawking particles, this radiation, we say that the black hole has a temperature. And an amazing thing is that the temperature of a black hole, sorry, here it should be an H, the temperature of a black hole goes as 1 over the radius of the black hole. I guess that everybody in this audience has already heard that the black hole has what we call the event horizon. The event horizon is this radius around the center of the black hole that if we are outside at a radius that is higher than this one, so for example, if we are here, we will of course feel the attraction of the black hole. But we can still turn around and go away from it. Run as fast as we can. We are allowed to do that. However, if we cross this critical event horizon radius, there is no way we can come back. Okay? And actually, the Einstein theory tells us that actually we will be pulled without mercy to the center of the black hole. No matter how strong my rocket is, or my engine is, I cannot escape from inside the event horizon of a black hole. Not even light, which is the fastest object that there is out there. And this is why we tend to say that the black hole is black, because not even light can escape it. Okay? And in particular, you know, the reason you are seeing me is because there is light from the lamp that hits my front head, reflects and goes and hits your eyes. If I try to do that with the black hole and I send some light to the black hole, the black holes don't have front heads, meaning that once the light hits the event horizon of the black hole, it is not reflected. It keeps going inside and never comes back. And that's why we cannot see it. Okay? But the important thing is that the temperature of the black hole goes as 1 over the horizon radius. Which means, this is really funny, means that the bigger the black hole is, the supermassive black holes are very large, have a very large radius. 1 divided by something that is very large is very close to 0. So supermassive black holes have a temperature that is very, very tiny. This means that it will be extremely difficult to ever measure this effect on a supermassive black hole. You see, you think, here I have an example of a supermassive black hole. With this guy I can do all the experiments and extract all the information I want from black holes, because it's so huge that there is no way, properties of the black hole will escape to me. But with the temperature you have this funny thing, The temperature, this Hawking radiation, is something that happens with tiny black holes, not with supermassive ones. Supermassive ones have a temperature that basically is 0, which means that the radiation is basically negligible. Okay? On the other hand, if the black hole is very tiny, then the temperature is large. Because 1 divided by, for example, take 1 divided by 0.1. This gives 10. Okay? So it can be large, the temperature in that case. So you see, black holes, on one hand, are gravitational bodies, which means that they are described by Einstein's theory, because Einstein's theory, like Newton's theory before, is a theory of gravity that describes objects that have mass, that have energy, and therefore create a gravitational force. But on the other hand, Stephen Hawking told us that they are also thermodynamic bodies. And they are thermodynamic bodies in the sense that there are these virtual pairs of particles, that is a quantum effect, that can become real and be emitted by the black hole. So, we have here a case where, and these quantum effects, they are present when the black hole is small, is tiny. Which makes sense, right? Because the quantum radiation, or the Hawking radiation, is something that is a quantum effect. Now, we know that quantum physics becomes important when we look to objects that are very, very, very small, of the size of an atom, or the electrons inside the atom. So it's for tiny objects. But you see, black holes are the first guys out there that at the same time, they can be very tiny, because you can have black holes of all sizes. But, and this is what does not happen with an electron or an atom, they can also be very massive. So for the first time you have an object that on one end is very massive, and therefore I need to use Einstein's theory to describe it. But at the same time it can also be very small, which means that I should also use quantum physics to describe it. But because it's simultaneously supermassive and tiny, I should in practice use a theory of quantum gravity. Quantum because it's tiny, gravity because it's massive. And this is the first object in nature that requires such a theory to be well described. And we still do not have it, the final form of the theory that describes quantum gravity. We have been looking for it, we have some candidates, but we have not yet an indication that these candidates that we have describe our world. Okay, they are, some of them, in particular string theory, for example, is a theory that mathematically is well formulated, has no pathology, let's say, but that does not mean that it describes the real world. Okay? Very well, guys. Let me tell you another property of the black hole, and this is the second formula, and I swear that I stop here with formulas, okay? But this formula is really beautiful. It's beautiful for two reasons. First of all, it's extremely simple. Trust me, you can have formulas. Well, I'm sure that at least 90% of you already saw formulas that look much uglier than this one. It is very simple. On the other hand, it has some it tells us a wonderful story. What is this formula? This formula gives you the entropy of a black hole. What is the entropy of an object? Whenever an object is a thermal object, is a thermodynamic object, thermodynamic means that there is some motion. Okay, we know that we get hot when we start running, right? When there is a lot of movement. If we start, if we are feeling cold, the first thing that we do is, we start, wrapping ourselves, we start running, we start making movements, So, thermodynamics is something that we associate it to motion. The motion does not have to be microscopic motion. It's, it can be just the tiny particles that we have inside of us, like the atoms, the molecules, that have velocity, and they are moving around and colliding with each other, and it's precisely when they collide with each other, actually, that they create temperature. Okay? But when they do this, because there is a lot of microscopic motion, there is also a lot of disorder. Can you imagine all of us now suddenly, there is a fire alarm, we don't know exactly where the door is, so we just jump from our chairs, and we start running, looking for the closest door around us, but we don't know where it is. We will start colliding with each other. That means that there is a lot of disorder. On the other hand, now everybody is well behaved. So now you are at a low state of entropy. Entropy is something that measures disorder. Microscopic disorder, typically. Okay? Now, black holes, because they are thermal objects, they emit radiation, they also have an entropy that measures the disorder of the black hole. Now, the amazing thing of this formula is that for the first time you will see that there are here K, index B, C, H bar, and G Newton. These are the four fundamental constants of nature. And this is the first formula ever that contains the four constants together. Okay? For example, E equals to mc squared. You already saw the C there. C is the velocity of light. 3 with 8 zeros in front of it, meters per second. Okay, you have that formula. That is telling you that you should use relativity in order to study that object, the motion of that object. On the other hand, K is what we call the Boltzmann constant. Is something that appears in statistics and actually in thermodynamics when you are trying to understand microscopically what is creating the thermal properties of an object. G Newton is something that that appears when there is gravity. Okay, in the 17th century we already knew this. Newton's law of gravity as a constant, that is the Newton's constant. On the other hand, H bar is something that we first saw in the beginning of the 20th century. This is the constant that appears in quantum physics. Now, the amazing thing is that in this single formula, you have the four constants of nature appearing together, which means that black holes, on one hand, they are gravitational objects because Newton's constant is appearing there. On the other one, they are quantum objects because the Planck constant, h bar, appears there. So this reinforces this idea that I told you before, that in order to really understand black holes, in the end of the day, Einstein theory will not be enough. We will need an improved version of Einstein theory that also includes quantum effects because h bar is appearing there. Okay? And if you want, this is the best indication that we have that there must be a theory that we still do not know, a theory of quantum gravity. Otherwise, it would not make sense to have a formula with these two constants, in particular h bar and g there. The other amazing property of this formula is that you will see that this formula is also proportional to something that I'm calling capital A H. H is horizon, the event horizon of the black hole. A means surface area of the black hole. This is telling us that the entropy of the black hole is proportional to the surface area of the black hole. It's not proportional to the volume, to the interior volume of the black hole. And this is per se a remarkable property of black holes, because usually the entropy, because it measures disorder, it wants to account not only what is happening on the boundary of our room. It also needs to know what is happening inside the room, in the volume, in all the volume of this room. It's not only what is happening on this wall. But in the case of the black hole, the entropy is just proportional to the surface area, not to the volume. This is one of the few objects in nature that has an entropy with these properties, being proportional to the surface area. But some smart people notice then that if the entropy is proportional to the area, not to the volume of the black hole, it is as if the information of the black hole is encoded, is encrypted, mainly on the surface of the black hole and not over all its interior. You see, it's as if, at least to study the thermodynamic properties of the black hole, it is as if, what really matters is what is happening on the boundary of my ball. Okay? And not what is happening inside. Of course, there will be little information contained inside. And if I really want to do a perfect, drawing of how the person looks like, in this case the black hole, I would not need to know how the interior looks like, But in order to get a good idea of the main properties of the black hole, I just need to look to the skin, to the surface area. That is enough. And this is remarkable because typically other objects require also the information that is on the interior. Okay? And this is where holography appears. Because it looks like that we don't need to know everything that is in the interior of a sphere, but I just need to know what is on the boundary of a sphere. But this is precisely what holography does for us, right? What is holography? Holography is we have, we all saw some movies, right, where you have a person and suddenly now the projection of this person appears in a two-dimensional screen with one dimension less, right? We have something that is three-dimensional, like me, okay? But I can have an holographic projection of me on this wall, okay? It's only two-dimensional, but it's as if I'm seeing the three-dimensional picture of the person completely. Although it's only two-dimensional. Okay? Is this clear? Does everybody have this image? I'm trying to pick a movie where this happens, there are... But you see, that holographic image, that usually it's in blue, if I'm not wrong, it's really two-dimensional, you see, it's really just a plane. But you look at it and it's as if, you are seeing something that is three-dimensional. Or in those books, right? Where we have to twist our eyes, Clearly the picture is in a two-dimensional page. But if we twist well our eyes, we can see some three-dimensional information popping out. Okay? And so that's what I'm trying to represent here. This is where the idea of the sphere that I showed you in the beginning appears. The boundary of the sphere, it's an holographic screen where most of the information is stored. And in particular, you have a screen And you see, although there are things happening in the interior, in the volume, that are really three-dimensional, my hand is three-dimensional, an apple is three-dimensional, but I can look into a two-dimensional screen and I see something that really looks like the three-dimensional version of it, although it's only two-dimensional. Okay? And now the amazing thing, and here there is a quantum leap, a quantum jump, okay, that I will not explain, but the amazing thing of this holographic correspondence between what is happening in the interior of a volume and something that is happening only on the surface of that volume is that the theory that describes the interior is the Einstein theory. It's a gravitational theory. But the theory that encodes, that describes in principle exactly the same phenomena, you see, because it's a projection of the apple, it's the projection of my hand. This theory that lives on this boundary, here the boundary, I'm putting it, it's planar, right? It's something like this wall. Here the boundary is a sphere. Okay? You can pick it as you want. It can be a plane or a sphere. But the important thing is that the theory that describes what is happening on my holographic screen is a quantum theory without gravity. And this is the amazing thing of this holographic duality, is that it's a correspondence, so it's 1 to 1. But this side of the correspondence is described by a gravitational theory, by Einstein's theory. On the other hand, what is happening on the holographic screen? It's a quantum theory without gravity. So you are saying that two theories that are apparently completely different from each other are related. There is a map, there is a dictionary that says this phenomena in gravity maps to this quantum phenomena. This is absolutely remarkable, okay? Because these two theories have nothing to do with each other in principle. But apparently they are related. And now the other quantum jump that I want to make is that quantum theories, in a certain limit, they have an hydrodynamic description. This means that, in a certain limit, this quantum theory that is living on this holographic wall describes the physics of fluids, or is described by the physics of fluids. Let me try to explain a little bit better what I mean by this. What I mean by this is that, imagine that you have a container that is full of gas. This means that you have molecules of oxygen or dioxide of carbon that are moving inside of this container. And they are moving with a certain velocity, that's what these arrows are. They eventually will hit the wall and be reflected back. And some of them will hit with the other molecules, okay? They will collide between them. These movements that are happening inside the box are extremely complicated. To start with, they are microscopic, so I cannot see them with my own eyes. I would need a really high-resolution microscope. On the other hand, they have velocities, okay? And it's really hard to predict what will happen when they collide. But this is, in practice, what is happening inside, for example, a drop of water. It's full of molecules that are colliding with each other. But in order to describe what is going to happen with my droplet of water, sometimes I really don't need to know what is happening microscopically. If I'm just interested on macroscopic properties of the water, for example, what will happen if I have here a balloon of water, and now I pierce the balloon, the water will fall and it will hit the floor, and I know what it will happen, and I don't need to know what is happening inside the water. So there is always a regime where molecular physics, which is describes what is happening microscopically, can be described by fluid physics. And this happens when I'm looking to processes, to phenomena, that happen in distances that are very large, this blue arrow, that are very large when compared with this typical distance between two molecules. So if I have here water, and I'm dropping it here, I'm talking about scales of the centimeter or the meter. On the other hand, the typical distance between two molecules, it's of the order of the angstrom or the micron or whatever you want. So it's very tiny compared with 1 centimeter or 1 meter. When I'm looking to scales of 1 meter or 1 centimeter, I can forget about the details of the molecular motion. And I use fluid physics to describe it. And I guess that now I have 5 minutes?
Yeah.
So let me tell you something that happens with water. And then let me tell you, to finish my talk, something that is very similar and happens with black holes. And then you will let me know if they are similar enough or not. Okay? So let me start by telling you something that happens with water jets. So if you have a water jet, okay, if this water jet, that it's a cylinder, it's a tube, this tube will have a certain length and it will have a certain transverse radius. Now if this length is very big compared with the transverse radius, this cylinder will start pinching off. You see, it will start squeezing in certain regions, while the other regions get lumpy. And at a certain point, completely pinch off will happen, and instead of having a tube of water, what you will have is an array of spherical droplets. Okay? This happens again if the tube is very long, which makes sense, right? Nature does not like to have things that are very long and thin. That's why in the bridges, for example, if the bridge is very long, you want to put vertical pillars quite often, although it's very expensive, to put them under the water. Because you know that if the bridge is very long, what you are doing there is that you are making the bridge, instead of being this size, in practice it will be of this size, because there will be a pillar here and another pillar there. Okay? Because if it is too long, it will break. That's also the same reason why glasses like this one are extremely expensive. Because they are very long, they are relatively thin, so the probability that they will break is very high. Okay? And this tells us an important property of water. For a given volume, give me a certain volume. And now I have a volume, a liquid, let's say water. And I want to take this water and I want to put it in many different shapes. I will pick a sphere, I will pick a cylinder. If you can do that, you will be a magician, but you can also make a pyramid out of it. I don't know how, but maybe you can do it. But the fact is that nature will always pick the spherical shape. And the reason why it does that is because for a given volume, the spherical shape is the one that has less surface area. So for a given volume, nature always picks the shape that has less surface area, less skin if you want. Okay? This pinch off is produced by a mechanism that we call an instability. And that was discovered by a British guy, Lord Rayleigh, in the 19th century, and Plateau, which was a French guy. Actually, it was the reverse. Plateau discovered it experimentally, studied it experimentally, made a lot of experiments and described what is happening. And then Rayleigh found the theory that describes this property that is responsible for this breakdown. Okay? The amazing thing, guys, is that Plateau was doing experiments with jets and with droplets, was measuring the distances, and he was 95% blind. Okay? Which is absolutely remarkable. And this was happening in the 17th century or 18th century. This is also the reason, it is precisely this Rayleigh plateau mechanism that is responsible for the fact that when you have a water tap and you open it, if you don't, the flux is not very high. If it is very high, you form a jet, and it will come out with full power, okay, and it will stay a jet. But if you don't open it if you don't open it that much, what will happen is that you will form a long jet, tube jet, that will pinch off, and will pinch off actually in an array of spherical droplets. This is also the reason, so you see it here, for example, it's this mechanism, it's this Rayleigh plateau instability. It's because water wants to adopt to be in a spherical shaped form, okay? This is also the reason why the rain is made of spherical droplets, okay? Because when it is produced up there, okay, initially it starts to be a jet, but when it arrives to us, it's a spherical droplet. Of course, gravity also helps pulling things away from each other, okay? But that's a second order effect. It's not the main effect. Now, to finish this, there were several experiments done with this, including in the outer space, okay? Because there was a point in which this instability was pretty annoying to people. Because do you remember the ink printers? The ink printers, what they do is they send a jet of ink, and then they move this ink of jet needs to move to make the letters, right? Now you see, you send a jet. If the jet breaks in the middle, you print part of the letter, but then there is a gap. Okay, and this is pretty annoying. So the companies that were producing the ink printers were really studying this in very much detail, at a certain point. Now let me tell you what happens with black holes. Black holes can also have a cylindrical shape. Okay? Not necessarily the black holes that we have in our universe, but certain solutions of Einstein's theory. If you are not just interested in solutions that describe the real world, the astrophysical world. So you can also have black holes that look like tubes. And the length of this black hole can be much bigger than the radius of the event horizon. And another British person, namely Ruth Gregory, that is a professor in Durham, in the north of the UK, together with Laflamme, that is a Canadian guy, they found 20 or 25 years ago that black holes also have a similar instability that makes them break into spherical array of black holes. And it's not just the images that are very similar. Any formula that you get from this Gregory-Laflamme instability, that is an instability that happens when you are studying the Einstein theory. It has nothing to do with fluids in principle. Any plots, any formulas that you get out of this Gregory-Laflamme instability match the formulas of the Rayleigh plateau instability for fluids. Okay? So this is a good example where you have two completely different theories. One involves gravity. There is this mechanism of the Gregory-Laflamme instability on a black hole. The other one involves fluids. No gravity at all. However, there is clearly phenomena that occur in one side and on the other side that are basically very similar to each other. Okay? And I think, William, that I should stop here. I could keep talking about other things, but this is a good moment to stop.
Dr. Oscar Diaz, thank you very much for... I certainly found that a very enlightening talk on a lot of aspects to do with black holes that I'd clearly misunderstood before, and Oscar's expressed them in a very accessible way that I think I could probably describe to somebody tomorrow. Anyhow, we're now going to take a break. If you want to go and carry out your own experiments with Rayleigh plateau affecting water jets, or alternatively the bar is open. Questions. The usual definition of a question is a short sentence or two lasting up to 30 seconds, ending in a question mark. Anything beyond that is an opinion. We invite a speaker for opinions. We invite you to ask the questions. Who would like to ask first?
By the way, you might have a question. It does not mean that I have an answer for it.
I was just thinking, it makes it for audiovisual aid, the soap bubble formulation, that when you create a little sort of foot diameter wire, you create a tube whirling around your head where it breaks into your demonstration. It would be superbly visual and dramatic.
Where's the question?
Thank you for that example of an opinion.
So if a virtual particle can if a pair of virtual particles can spontaneously appear, can they spontaneously disappear? Are they linked together? And what happens to the one that's inside the black hole if they spontaneously disappear?
That's a very good question, and so good that it's an open question. So that's one of the driving forces in our field. We are trying to answer questions like the one that you just raised. Because they should be, we have a word for that, they should be entangled. There should be some connection between them, because they were produced, originally, they were produced together. They had a connection, so this connection should not be lost. However, Hawking radiation, in the end of the day, it's very thermal. Being very thermal means that it's very monotonous, meaning that any thermal radiation has a spectrum that is the same, no matter the origin, the body that is producing it. As long as it has a temperature of, let's say, 100 degrees or 10 Fahrenheit or whatever measure you want to use. If it is a black hole with that temperature, or it is, an engine of a car with that temperature, the radiation that it will produce is the same. Is absolutely the same. And this raises the question that you are asking, which is, but clearly, the origin of the thermal radiation in a black hole is very different from the origin of the thermal radiation in an engine. And in particular in the black hole, can I make a connection? Can I know what is happening to the other half that was swallowed by the black hole or not? And people do not have yet a definitive answer for this. And the reason why we don't have a definitive answer is because we still do not have the appropriate theory to address that question. That appropriate theory is the theory of quantum gravity. That we still do not have it, the final theory. Okay? Only that final theory will allow us to have a clear answer. But it's really one of the driving forces. You have a lot of papers on this subject nowadays as we speak. Okay? And there is even something that is called entanglement entropy that is related with that question.
Another question?
On your back?
Is the theory being developed? Well, no, sorry, let's start again. You've described theories, I think, which there isn't at the moment any real physical substantiation. So is the emphasis of the work that people like you do, is it trying to develop experiments that will show that the theory is right, or are you still mainly advancing the theory?
So the problem with black holes, and in particular with quantum gravity, is that as I tried to explain before, you need at the same time to have something that is very massive and very tiny. And you don't find that on the Earth. No. This is something that you can find things that are very tiny. For example, you look to the interior of atoms. Okay? But this is not supermassive. On the other hand, if you want to find something that is supermassive, you need to go to the outside the Earth to find the supermassive black holes. The combination of the two, it's really difficult to find in our daily life. So we cannot really do experiments, at least controlled experiments. We might, if we are smart enough, maybe one of these days we will have good detectors that can scan a certain region of our outer space and find, some events occurring there that involve tiny supermassive black holes. But we are still very far away from that. So we have to live with the theory at this point. That's essentially what we are using. We are trying to develop the theory. This is one of these cases in which it will be very difficult to have help from experiments. We will have to develop the theory first. And then, if we are lucky enough that we get the right theory, then we can eventually design some experiments, some very clever experiment that can test the theory. Okay? Let me say it in other words. Einstein's theory was developed well before the experiments. It was later confirmed by experiments. Those experiments, some of these experiments were so difficult that it took 100 years to detect it. That's the case of the gravitational waves that I was describing, that were only discovered 2 years ago. 2 years ago, Einstein's theory of gravity was formulated in 1915. 2 years ago, it was 2017. Well, I think that the detection was 1 or 2 years earlier. Okay? So it took 100 years for us, even with a gravitational theory that is simpler than a quantum gravity theory, to design the experiment and develop the technology that was necessary to detect the consequences of the theory. With quantum gravity, it will be very much like that, or even worse. Which makes it also very hard to get there, because we don't have help. You have an idea, let me test it. Let me go to the lab and test it. This was in the old times, this was the good way of doing physics. We don't have it here.
I've got the microphone, but...
Hang on, just a second.
With the recent imaging of the black hole, where they telescopes all that around the world, has that revealed any more information about measuring the heat radiation? Or
Not yet. So he's talking about something that is called the Einstein telescope, which is an experiment that is trying to photograph between commas a black hole. I told you that you cannot really photograph a black hole, because in order to photograph, what I have to do is what I told you before. You need to send some light to an object. That light hits the surface of the object, gets reflected, and comes back to your camera, that then registers this light. Now, if you try to do this with a black hole, whatever hits the black hole, once it crosses the event horizon, it will not be reflected. Okay? It will just be swallowed. So you will never receive back the signal. So people are trying to develop alternative ways of photographing a black hole. That alternative way of photographing a black hole is the following. If you have a black hole, and this black hole is not isolated, if there is what we call an accretion disk around it, that accretion disk can be moons or earths that are orbiting, or that video that I showed you before. There are stars going around the black hole. In the same way that there are stars going around the black hole, if you could have a really good camera, you would see that even closer to the black hole, you also have, clouds of dust, of galactic dust, that are orbiting really around, very close to the black hole, and some of it is being swallowed by the black hole. Slowly as time evolves. One piece is swallowed now, another piece later on. But what people are trying to do is that this dust that is around the black hole, like, I don't know if you saw the news, but have you seen the news yesterday of Delhi in India with all the smog?
Yeah.
So, you see what I mean by photography. If you try to send some light to this, you will see that there is a cloud there. And so what people are trying to do is they send some light, okay, if you want, and that light will not be reflected by the black hole, but it will be reflected by the dust that is around it. Okay? And eventually you will find, you know, a center that is very dark. That's the part that cannot reflect light because there is an horizon there. But the surrounding reflects it. So you see the surrounding, but then you see a black spot in the center. So this is what this Einstein telescope experiment is trying to do. They already have some images, but they are at the very beginning. So now they will have to, you know, understand very well the data that they are receiving in order to, in the future, they can start fine-tuning. You know, up to now, you know, the images that they have are not telling us nothing special, nothing that new. But they are starting, okay? They first need to calibrate, if you want, the experiment to see that it's working, okay? You are getting what you would expect. Then let's try to look for details.
Another question, yeah?
What is the predicted ultimate fate of a black hole? What is it going to do in the future?
So this depends on the type of black hole. So for example, if you have a supermassive black hole, like the one at the center of our galaxy, basically what this black hole will be there forever, I guess. Forever meaning at least while the universe is expanding, if it does not contract one day. But this black hole will just get bigger and bigger because it will keep swallowing more and more accretion matter that is around it. On the other hand, and also remember, this supermassive black hole has a very large event horizon radius. So it does not emit a lot of thermal radiation. When you are emitting thermal radiation, you are losing energy because you are emitting, you are losing something. Okay? But supermassive black holes, they don't emit a lot of thermal radiation because the temperature is 1 over the event horizon radius. So it will not lose weight because of this quantum effect. On the other hand, it will keep whatever decides to cross on his way will be swallowed, so it will get fatter and fatter, bigger and bigger. On the other hand, if you have a tiny black hole, the opposite will happen. Because a tiny black hole has a very small horizon radius, and so it has a large temperature, meaning that it's emitting a lot of thermal radiation. But if it is emitting thermal radiation, it's like some water. It will evaporate. It will, you know, when it is emitting, it is losing energy. So it will get even smaller and smaller and smaller, instead of getting bigger and bigger and bigger. Of course, if it is tiny, but it's, you know, it meets this mug, of course it will also swallow the mug without any problem. But if it is very tiny, it can happen that it's a tiny black hole that is in a region of our universe that does not have stars in the nearby region, and so it can spend a long time before it meets something that can eat, that it can swallow. During that path where it is alone, it is emitting thermal radiation, so it will evaporate eventually. How exactly will it evaporate? So what will be the last stages before it completely disappears is something that we do not know. Why don't we know? Because again, we don't have the final theory of quantum gravity that would allow us to address that question. You know, because the black hole is so tiny, you need to have the quantum update of the gravitational theory of Einstein to address the details of your question. You see? I don't have the theory. If I don't have the theory, I cannot find the solution. First I need to have the theory, and then I look to what are the solutions of the theory. Finding the solutions of a theory, of an equation, sometimes is not easy at all. But it's even more difficult to find a solution of an equation that you still don't have. And we still don't have the equation that describes the quantum gravity theory, that describes massive black holes that are tiny. So tiny that they have a lot of thermal radiation, and they are evaporating, they are squeezing. What is the end point of such objects? We still do not know. But again, it's a question that we keep asking. It's driving us. You know, it's questions precisely like yours and the one that we asked before that are making us think about the theory.
Thank you. Question about your two formulae that you presented. As far as I can see, they seem to be likely to be describing the surface properties of the black hole, and are they and the only property that we know of a black hole at the moment is the Hawking radiation that we can measure, which I imagine can be regarded as a surface property, since the amount of radiation that is generated relates to the surface area. Therefore, I think it's not surprising to find that one of the descriptions is proportional to the surface area, which I think you pointed out in the second of the formulae. Are those formulas only trying to describe the Hawking radiation property of the black hole?
So let me tell you, I'm telling you that this formula in particular, on one hand it has the Newton's constant, which means that this describes the gravitational object. On the other hand, it has h bar, which is Planck's constant, which means that this object must be described by quantum physics. How did Hawking get this formula if he does not have the theory of quantum gravity? Because this involves gravity and quantum physics. This is an explicit formula, very clear. It's not even approximate, it's equal. But we don't have the theory of quantum gravity. So how did Hawking get this? He got this because he did an approximation. When we don't have the exact theory, we can do what we call perturbation theory, which is you start with a background that is just described by the gravitational theory. In this case, it's the black hole. The black hole that Hawking used was a black hole that is a solution of Einstein's theory, without quantum physics at all. Then what he did is, let me now consider some tiny quantum effects around the black hole. But they are tiny, so that the original solution is still well described just by the gravitational theory of Einstein. But then I consider some quantum physics, but tiny quantum physics around it. What is that tiny quantum physics? It's, for example, a particle and an antiparticle that originally is a virtual pair, okay, and that gets created, and then typically it would be annihilated immediately after, but because there is this gravitational field, it can be pulled away from, the two particles can be pulled away. But you see, this, it's a very tiny effect compared with the bulky black hole that you start with. So you don't really need the full theory of quantum gravity to understand phenomena like this one that allows you to derive this formula. But this is still this is only an approximation, a very rude approximation, where you start with a background that is just described by gravitational physics, by the gravitational theory, and then you consider a tiny quantum effect on it. But this is already enough to allow you to find this formula, although you still do not know the full theory. Is this answering?
You describe it as an exquisite formula, but surely it's only exquisite if it can be proved to be correct.
Oh, absolutely, absolutely. No, absolutely. We have not proved it. You know, that's what differentiates physics from mathematics, for example. Okay? Physics, you know, you can have mathematical theories that are wonderful in the sense that they are consistent, self-consistent. You cannot find any contradiction. As you keep studying it, you will never find a result that contradicts another result that is predicted by the theory. But you can have, let's say, 100 beautiful theories that are candidates for a theory of quantum gravity, for example, but only one of them will describe the real world where we live. And to know which one of these 100 is the correct one, you will need to do an experiment. You will need to compare the predictions of these 100 different theories. They will predict different things, different results for certain experiments. And it's only when you do the experiment that you will say, oh, it's this one that is the correct one, because it's that theory that is predicting the right result. Okay? And that we don't have, and we will not have in our lifetime, for sure. Because this will involve, again, things that are very heavy, but at the same time very tiny. There aren't many objects out there with these properties. It's only the black holes, really. And the black holes, as I'm telling you, we are still fighting to find one. We have not a direct observation of a black hole. We have indirect observations. For example, the fact that we have detected gravitational waves, we can see that these gravitational waves have the characteristics, the shapes, if you want, and the frequencies of the gravitational waves that are produced by the collision of two black holes with certain masses and rotations, which are predicted by the Einstein theory. So you can compare the properties of the gravitational waves that you detected with the properties of the gravitational waves that the Einstein theory predicts, and you see that they match. Okay, so this is telling you that indirectly black holes should indeed be objects that exist in the real world. But you are not observing them directly. Again, it's through the gravitational waves. In the end of the day, you will need to have tiny black holes so that you can have quantum effects, strong quantum effects on it. And this will not be easy. First, to find them, and second, to have them in a controlled environment where you can study them in detail. Okay? Because it will be very difficult to cage them inside of a room or a container. Okay? And I cannot imagine that happening in my lifetime. Not even my grandson. Okay, probably. It will be extremely challenging. People will have to be extremely clever.
I haven't understood. What does it mean to say? What does it mean to say that a black hole has a certain radius or a certain surface area? What does that mean?
So the radius of if you want, a black hole has a certain energy or a certain mass. You agree with this? That you can accept. Now, if you have a certain mass, the mass in the end of the day is proportional to the volume. For example, if I tell you, look, I have here 1 kilogram of water.
Why? Why is the density of the black hole constant?
No, the density of a black hole is not constant. But the fact that you have an energy tells you that that energy must be contained in a certain radius, in a certain volume. And the Einstein theory tells you what this radius is, or should be. Okay? And then, that same theory predicts the existence of gravitational waves, for example. And you have already detected gravitational waves that have the characteristics that are predicted by the Einstein theory. So you know that the Einstein theory, at least with respect to the gravitational waves, is correct. So your best hope now is that if it is correct on gravitational waves, but also in the eclipse, you know that there were also 2 or 3 other experiments in the past, in the 20th century, that confirmed the predictions of Einstein. So if the Einstein theory, in those very few experiments that we could do, match the results of the experiments, that makes you get strongly convicted that, okay, what the rest that the theory is predicting that I have not yet observed experimentally should also be correct. Because the tests that I could measure, the tests that I could make up to now, the theory passed all of them. Okay? So hopefully it will pass the other ones. And you know, and the theory predicts that a black hole should have a certain radius, a certain horizon radius. It appears explicitly there, you know. You have something that is 1 minus, you know, the energy divided by the radius. And this 1 minus the energy divided by the radius gets 0 when the radius is proportional to the energy, is equal to the energy. And this is precisely the event horizon. It's when something goes to 0 in the theory. You know, and this is a formula, an explicitly formula that describes the gravitational field of a black hole.
You sparked a million questions, I think, in my mind, but that formula would imply that the mass of the black hole is proportional to the surface area.
No. So
why not? Because E equals mc squared, so you can substitute c squared for E over m. So mSPH equals 1, whatever it is, E, C, and AH. So it's directly proportional.
No, but it's also proportional to what you are proposing is that I go here where it is c to the cube, right?
Yes.
This
yes.
is c squared times c, and now
Yes.
the c squared is energy divided by m.
Yes.
Okay, but remember, all of this, you still have the entropy there, and you still need to compute the entropy. So it's not that the energy is just proportional to the area.
But it is a formula where E, where the mass is to the same power as the area. It's not a multiple to a square or a cube. Whereas in a normal sphere, then the mass would be related to the
Oh,
square
absolutely.
of the
Yeah,
surface area.
absolutely, absolutely.
So that's a very unusual relationship, isn't it?
Absolutely, absolutely, no doubt about that. No doubt about that. And in particular, you know, for example, in black holes, I was telling you, in the case of, so the fact that the entropy here is proportional to the area, I told you about certain properties in black holes that are similar to the fluids. But for example, in fluids, I also told you that the rule is that for a given volume, the nature picks the configuration that has less surface area. For the black hole case, the statement is for a given energy, not a given volume, it's a given energy, the black hole will pick the configuration that has the highest surface area. Because this is the one that has the highest entropy. That's what the Greg-Laflamme instability tells you. You start with a tube that has a certain energy, you will end up with the same energy, but distributed over spherical black holes. The area, the total area of these spherical black holes is higher than the area of the initial cylinder. It's not smaller. With the water, it was the opposite. So this is to tell you that black holes behave very differently from standard objects we are familiar with in our daily life. And all of this goes back to the fact that entropy is proportional to the area, not to the volume.
Can I ask a slightly offbeat question? Does that mean that the black hole is related to a string theory?
Which one? This formula?
Well, if it's proportional to the area, that would be the end of a tube, would it not? But it could be the end of a string, so each black hole is a string, not a sphere.
Not this relation. I would not say that this relation is telling you that. Although what you are proposing, you know, the idea of string theory is that the vibrations of the string. So when you have, for example, a string in a guitar, you can play the string, and when you pull the string, you will excite certain frequencies. Exciting certain frequencies means that you are exciting certain energies. Because one of the relations of quantum physics tells you that energy is equal to h bar, this h bar here, times the frequency. So give me a frequency, I multiply it by h bar, and this gives me the energy associated with that wave, with that frequency. Okay? And the spirit of the string theory is particles, localized particles, do not really exist. What you have is little tiny strings that can vibrate with certain frequencies. And it's the characteristic frequency of the string that gives me the energy of the particle. And it's that energy that can harm me. For example, if it is a bullet, it has a certain energy that when it hits me, kills me. That energy of the particle is ultimately associated with the frequency of the tiny strings the particle is made of. Okay, so it's not really the area of the string that really matters. It's the typical frequency of the string that matters. It's that gives you the energy. Okay, you are more thinking on kind of the surface area of the string, right? Or the cylinder, or the end of the cylinder, the basis of the cylinder. But it's not, in string theory, it's not that gives the energy. It's the vibration frequency of the system.
Time for about one more, I think.
I understand that information is indestructible. What happens to information carried by the material that's absorbed at the event horizon?
That's one of the questions that it's an open question that we need quantum gravity to solve it. So in particular, look, the amazing thing of what we know nowadays is that if we throw a stone that has 1 kilogram, or if we throw a book that has the same 1 kilogram, in the end of the day, the radiation that is emitted by the black hole is the same. That's what I was telling you before. Unfortunately, the black hole, if it has a certain energy, independently of how you form the black hole, the radiation that it emits, it's very monotonous, meaning that it's the same as the spectrum, the emission of spectrum that is emitted by another object that it's at exactly the same temperature. So this means that if you have two black holes that have exactly the same properties, the same energy or the same mass, the same spin if you want, but one of them was formed by piling up a lot of stones, and the other one was formed by piling up all the books of this library. Once they are formed, when they evaporate, when they emit this thermal radiation, they will emit exactly the same thing. So you may ask, what the hell? So this guy is made of stone, so it should be dummy. It should not. And this one, it's full of information. So they should, in the radiation that is emitted, I should see a difference between the two. And in particular, I should be able to recover the information that I send. How this happens, we do not know. This is one of the open questions. And in particular, this is highly related with quantum physics. Because quantum physics is what we call unitary, which means precisely that you can always recover the information in the end of the day. But with a black hole, it looks like that the black hole is not unitary. It is not allowing you to recover that information. So how do you solve this? It looks like that we have a paradox. A black hole can violate one of the most fundamental principles of quantum physics. On the other hand, in the end of the day, we want black holes to be described by quantum gravity. So they will have to be quantum objects that respect the laws of quantum physics. So how do you reconcile these two things? And that's one of the major, open questions. In this search for the final theory of quantum gravity, it's precisely questions like yours or the one that we had before, that are the driving force that we keep always present in the back of our mind. Hey, the final theory will have to address this. So whenever I see an opportunity to address that question, even if I don't have the full theory yet, but if I think that I have a good candidate, let me see which answer it gives to that question. Yeah, but the answer is we don't know.
Okay, I think we better bring things to a close there. Dr. Scotius, thank you very much again for a very enlightening talk and very stimulating question and answer session. I don't think we've ever had a session where quite so many people have stayed on after the talk for the question and answer as well. So please give Oscar a very big round of applause.